In chapter 18, we are going to briefly go over how reactions can happen at different rates. So we'll just talk about the effects of rate reactions, or reactions of rates of reaction. And we will talk about equilibrium and how there are stresses that are added to reactions at equilibrium and how that is overcome. So some reactions happen really quickly, like when you strike a match to light it, that's a really quick reaction. And others occur very slowly, like plant material converting into coal. So the speed at which reactions go can vary from very fast to extremely slow. Speed is an example of rate. So a rate is a measure of how much something changes within a specified amount of time. So the interval from time can vary depending on less than a second to centuries. In chemistry, we like to do it in like seconds or minutes because we don't have centuries and we won't be able to see it if it's less than a second. So we study reaction rates, the rates of a chemical reaction in chemistry class. Um, and this is usually expressed in the change in the amount of the reactant or product per unit time. So the amount of a reactant is usually expressed in moles. That's an amount that's very applicable for chemistry. We've been using moles for a very long time now. And over time, the amount of reactant decreases and the amount of product will increase. So this I have as an example for this reaction. Um, the two NO2s have, they're reacting together in a combination reaction. So you see how in the picture they're circled. So A, B, and C pictures go with this reaction over time. In models, usually oxygen is red and nitrogen is blue, hence the colors. It looks very similar to water though, doesn't it? So they have them circled so that the circled spots are the reacting molecules. And so in A, it's only reactants at the beginning. But as you can see, then the circled molecules will then react and turn into the products to the NO, two NOs and one O2 kind of thing. And so as time progresses, more and more products get made. We would assume that that would happen, right? That is how we know reactions happen. Well, a model that we use to try and discuss how chemical reactions actually occur is called collision theory. According to collision theory, the atoms, ions, and molecules involved can react when they collide if the particles have enough kinetic energy. So this is how we explain, using this theory, how reactions take place. But it's important to know that things don't always react when they collide. So particles that don't have enough energy to react will bounce apart unchanged when they collide. So this picture I have here is just a summary of how the conditions that you need in order for reaction to happen. So the first picture has reactants moving too slowly. So that means that they don't have enough energy. Okay. And so then they're going to react and bounce away unchanged. Then the middle one, reactants not facing the right way. This is called like either arrangement or orientation. So if the molecules are not in the correct arrangement when they react, then nothing will happen either. So even if they have enough energy, then if they're not arranged properly, when they collide, if the right parts don't hit together, nothing's going to happen. So in order for a chemical reaction to occur, you have to have both enough energy, enough fast movement, and the molecules need to be oriented properly. If you look, I know it's kind of hard to see. I know the picture's kind of blurry, and even on your paper, it's kind of in black and white. But um, what's happening here is it's NO3 reacts with CO, and the CO will pull away an oxygen to make CO2 and leaving NO2 left over. So if the oxygen hits the NO3, nothing is going to happen because that oxygen doesn't need to go onto the NO3 and it doesn't need another oxygen. It has to have the carbon hit it in order for it to occur. So those are the two things that need to happen. So talking about that amount of energy that's required for the reactants to actually react, we call that activation energy. This is almost like a barrier that the reactants have to cross before the products can form. So this is called an energy profile diagram, where there's lots of information here. The reactants are always at the start because as the reaction progresses, we always start with reactants first, right? Products are at the end. Now, the products could be lower than the reactants on the graph, just like it is pictured here, or it can be higher. The position of it has to do with what we learned about in chapter 17, the heat or the heat of reaction, or the enthalpy. Okay, so if it is a endothermic reaction, then the products will have higher energy than the reactants, and so the products would be written above. But this would be a case of exothermic because the products have lower energy than the reactants, which tells us that energy was lost or released. Okay, so that's tying in chapter 17 stuff. Well, this new activation energy, that is the height from the beginning height of the reactants up to the very tip top of this graph. This amount right there, if you subtracted those 2 points on the y-axis, that would be called your activation energy. And sometimes we use EA to signify activation energy. So if it doesn't have at least that much energy, it's not going to be able to get over the hump to turn into products, so nothing is going to happen. When the two reactant particles collide, they may form what's called an activated complex. So the activation energy is that minimum energy required, right? So then the activated complex will form only if they're arranged properly. So the activated complex is an unstable arrangement of atoms that's just like they kind of like smush together when all of the reactants collide together, and then it will break apart. So the spot on the energy profile is at the very tip top spot of the energy profile. So once it has enough energy at the very tip top of that peak, that's when the activated complex comes together and happens momentarily. It just arranges briefly before it splits off again. So the activated complex can only be there if they have enough energy, and then if they're oriented properly. So it's not going to happen if the wrong parts collide together. Okay, and we call this a transition state. It's not included in the reactants or products because it is something that just happens very momentarily. So in this picture, I have first, this is a reaction to make water. Okay, so we've got hydrogen gas and oxygen gas, and so when the activated complex forms in the second picture, then everything's just smushed together. Do you see that? And when it's smushed together, then all the atoms can start to spread apart, so that when it breaks up in the last picture, then that is how we get our products. So that's a little bit more about the activated complex. Okay, so we want to draw an energy profile diagram given the information we have in order to show how the energy is for this. It's actually not a reaction, but it's a phase change, turning gaseous bromine into liquid bromine. Okay, so the reactants and the products. Reactants always start first. So this is really the reactant. This is really the reactant, okay, R for reactant. But I like to put it, if I know what it is, I like to put that down. So we got Br2 gas as our reactant. Now our product, the Br2 liquid, we're going to place that, but it all has to come into was whether this was an exothermic or an endothermic reaction. Well, looking at our delta H, we can know right away. Since it has that negative sign, we learned in chapter 17 that negative means exothermic. So that means that the height of the products is going to be lower than the height of the reactants, and it's actually going to be 31 points lower. Now, we don't really have a scale to draw to, so we're just going to make it lower and say that that difference is 31, equal to 31. Okay, so just pick somewhere lower. That's your product line. So this is for products, okay, which is the Br2 liquid. And so the height difference, we can label this right here, and I'm trying to line it up to be the reactant height to the product height. That is our change in enthalpy or heat of reaction, which was negative 31 kilojoules per mole. Okay, well, this isn't complete yet, but this is all the information we're given. We can still add some more stuff, okay? So every energy profile needs a peak. So this is where you have to just get a little creative, okay? And you're gonna draw your peak. Your peak can go as high as you want to, but then you have to come back down and finish it off where the products are, okay? And then we can label, we don't know what the value is, but we can label from the height of the reactants up to the tip peak. This right here is the activation energy, EA. You can also write out the words activation energy if you want to. And last but not least, at the very tip top, we have our activated complex. That's where the activated complex comes into play, at the very top of the peak. Okay, so that's as much information as we have for that. In our homework packet, we've got some more things to do, and I'll make sure to tell you all the things you need to include each time. Okay, so along with having enough energy and having the right orientation, then we have some other factors that affect the reaction rate, because every reaction proceeds at its own rate. Some are very fast and some are very slow, like we said at the beginning. So you can usually vary the conditions to modify the rate of the reaction. And so we can modify that by changing the temperature, changing the concentration, changing particle size, and using a catalyst. So first of all, let's change temperature. We know that usually raising the temperature of a liquid or of a substance will speed up the reaction because of higher kinetic energy, and lowering it will slow it down because of lower kinetic energy. So when you're raising and lowering the temperature, you're changing how fast the particles move. And if we have collision theory and the particles are moving faster or slower, that will change the frequency of the collision. So if you are raising the temperature, that would increase the frequency of collisions, increase the kinetic energy, so increase the rate of reaction. So the products would be able to form faster when the particles move faster. The next type of change we can modify a reaction rate with is by the concentration, or the number of particles, or the amount. So when particles in fixed volumes change their amounts by increasing the concentration, the reaction can happen faster because the frequency of the collisions will be faster. This picture I have here is just trying to show oxygen is a reactant in combustion reactions. We should know that from chapter 11. And so the left picture is showing how there's hardly any oxygen present, but then the right picture, it's burning a lot brighter, so that means that there's more oxygen present. So when you have more particles, that increases collision frequency, which leads to a faster or higher reaction rate. The next type of change is particle size. So we probably know this from like melting butter or something, that the smaller the particles, the faster things can happen. So usually we think about it with surface area. When you have lots of smaller particles instead of just one big particle, the surface area will get bigger. So the greater the surface area, the better results you have for a faster rate. So you would want to increase the surface area, meaning make smaller particles, break it up to make the reaction happen faster. Another way to increase the surface area, or to make it get smaller particles is to dissolve it. We have solutions and we've been using them all year because solutions react a lot faster than solids. So in solutions, the particles are separated already. And so then that makes them more accessible to the other reactants to move around and to collide. But if a solid cannot be dissolved, sometimes it can be ground into a fine powder to increase its surface area. Last but not least, the last change that we can make, because sometimes changing the temperature or changing the concentration is not always the best way. So maybe we need to use a catalyst instead. So we have the term catalyst before this year. It's something that will increase the rate of reaction without being used up. So catalysts permit the reactions to proceed a lower energy path, which allows the reaction to need less activation energy to form the products. So what happens on the graph, and I know that yours is probably in black and white, is that, you know, that hump from the activation energy that we had on our energy profile diagram, that hump gets lower when you have a catalyst because it doesn't need as much energy anymore. So this is in red, and the dotted line is that lower hump. So that's something that you just need to know, is that the catalyst lowers the hump. And I might have you draw that on one of the energy profile diagrams. Okay, so also it's important to note that a catalyst is not consumed during the reaction, so it doesn't appear as a reactant or a product. It'll usually show up as something written over the arrow as a catalyst. And it might not even say the word catalyst, it just might be there. And that's because it's not a reactant and it's not a product. It's just there to help. If anybody is in Mr. Whiteloff's classes where they make the hydrogen fuel cell cars, that reaction needs a catalyst in order for the water to decompose into the hydrogen gas and the oxygen gas. And the catalyst that's used in that is a plate of platinum metal. So where it says FeCl3, for that reaction, you would put PT there because that is the chemical catalyst used. So those are all ways that we can change rates of reaction.